All right, I'm a teacher in the Eastern Sierra. We're going to go camp in Yosemite for a few nights and have to do some lessons, so I'm the math teacher. I have to teach a math lesson. Luckily, I remember that Vihart has some really cool math videos about Fibonacci in nature, so I start watching one of her videos. And I go through it and I'm like, oh, this is excellent. This is what I'm going to be teaching my students. Oh, she talks about spirals, and there's a bunch of different types of spirals. So I decide to play with it to make sure that I understand it. I go to Scratch where it's really fast to make things, and then I do things. I'm like, okay, well, I have the three different types of spirals, and they're pretty straightforward to code. And they're really fun. When I'm doing my spirals, I'm not thinking too much. I'm just having fun and making sure that my students will have fun with me, noticing the different type of spirals. Scratch is usually the first place that I go whenever I do new coding projects because it's just so fast to code. I decided to do all the different types of spirals. They're super mesmerizing. My students are always impressed. I leave it up on the board. This is the type 2 spiral, the slug cat pattern. I think I need to add the code so that I have the ears, the eyes, and the mouth. And I'm going through all these spirals, and eventually I start going down this rabbit hole of how cool it is to code and how fun it is to do stuff with math. I think I'll link all of these to the description if you want to see any of the cool programs. I mean, they're pretty straightforward. And then you do the third type of spiral, but I had a problem with this. When I did my third type of spiral, the code was sloppy. I just have it turn by a random angle and then move forward and then keep going out, and it didn't really work. And then I tried doing a bunch of different things. You can see my code to do the third type of Fibonacci spiral. I eventually decided to just move it by a random angle and then change the distance by a little bit and get bigger and bigger, but I couldn't figure out a way to make it so that it would grow by a Fibonacci spiral. This is just like a random, maybe a logarithmic spiral. I'm not sure if that's technically a logarithmic spiral, but it looks like the one that she mentions in her video. So then she moves on in her video and talks about how she's supposed to arrange petals. I think it's like in video number 2. Let's go ahead and go back. In video number 2, she's talking about how petals are arranged and how they rotate by 1/5 of an angle, and she talks about how to actually generate those patterns. It's somewhere around here. Oh yeah, so she just keeps adding petals at the random angle. I'm like, okay, well, that's going to be super easy to code, and I go ahead and I do that with a really simple program. I'm like, okay, so if I just hit spacebar, I should see the petals forming. The one thing that Vihart does in her video that I did not do is she color-coded her leaves so you can see the spirals forming much easier, and I just chose a random color because I'm lazy. Maybe I'll go back and change that. But it's really cool. You get to see the spiral pattern. You can see these leaves spiral in. So like this purple, I'm colorblind, I think purple, then green, then red, then purple, then green. Like you can see that this is a nice spiral. But then I realized that my students would struggle to identify spirals in pine cones. I know when I first did it, it was really hard. So I'm like, okay, well, I want to invent something where they can like look at dots and see the spirals, how they can spiral one way or they can spiral the other way. You can see there's like a spiral this way as well. So let's start with dots, and then I'll upgrade to like real plants when we're out there in nature, out there in Yosemite. So then I'm like, okay, let's go to Scratch again. It's the easiest place to go. And I go ahead and I make a quick program. I failed my first few attempts, but I eventually get a bunch of dots to work, and it is a Fibonacci spiral. I made sure to use the complex number system in order to make sure it worked out perfectly, and it looks beautiful. I'm like, okay, that's perfect. But the problem is, as you saw, this thing, it took a long time to generate, and I want to do this for like really big spirals. I want to zoom in and zoom out, and then I'm like, okay, Scratch, I think I'm done using you. I'm going to go ahead and use GeoGebra. And I know GeoGebra pretty well, but I taught myself some more. Essentially, I first started by doing a list. You can do this command: list is equal to 0, ... and then whatever number for the end of your list, and then cool, you got a list of a bunch of integers, right? And then next you can say, okay, I basically did the same exact code that I had in Scratch, where I'm like, okay, cosine of that list times a random angle, and then sine of a random angle, same exact complex coordinate system. And it made the spirals, and I can zoom in, I can zoom out. Sorry, that's zooming in and that's zooming out, and it was mesmerizing. Like you can hit play on this thing, and I think I watched like a number file video a while back where they watched this thing rotate, and it is really, really fun. And because I'm recording the screen right now, it's really difficult to record and do this. It's like lagging like crazy. Again, I'll probably link this to the description. It wasn't that hard to make. It took me like 5 minutes. And then you see all these cool spiral patterns. And then I'm trying to figure out, okay, well, why is it sometimes you can see a clear number of patterns, and then if you zoom in, you see a different number of spirals, like where did those number of spirals come from? Are those Fibonacci numbers? Do they build on each other? They add on, like if I see 3 spirals and then I see like 5 spirals, is the next number going to be 8? It is always the case. And I did some math and went down another rabbit hole, and I'm like, okay, that's never the case. Well, that's almost never the case. I thought that would be the case because I watched this video back over here where if I come over, does it give me my suggestions? No, there's like a, here, I think my suggestions will be renewed if I go like this. Yeah, there's the Mathologer, the fabulous Fibonacci flower, and he talks about the geometric pattern, how you can add the spirals and then go across the diagonals. I'm like, okay, so they're just adding on each other, and that still didn't satisfy me because that didn't work. So then I'm like, okay, I'm going to pick a random number, and I use the slider to slide this thing to 130 degrees, although and that's not the true story. I accidentally slid this to 130.1. I'm like, okay, I counted the spirals. I zoomed all the way in, and I counted, okay, at the very inside there looks to be 3 spirals, and then I zoom out a little bit, and if you count the next spirals that come out like to the clockwise direction instead of the counterclockwise direction, there's 11 of these spirals, and then if you zoom out really far, then there's, it took me a while to count them, I'm bad at counting, 36, and then no matter how far you zoom out, if I changed my list to 10,000, no matter what happens, these lines just go on and on forever and ever, and they never make a new spiral, which was interesting too. Like, why did it stop there? I had my suspicions. I assumed that it was getting closer and closer to the next perfect rational fraction, and I decided to do that. So the only way that I know to get close fractions is using continued fractions to approximate that. So let me turn this list back down to a reasonable number so it doesn't slow down my video at all. The way that I did that was I said, okay, what if I have a rectangle that's 130 by 360? So I can go ahead and do this with you. If you've never done this before, you should definitely give this a try. It's a great way of doing continued fractions, which are great ways of approximating whatever ratio that you're looking for, like if you want to approximate ratios for pi and stuff like that. The general idea is you have a point. So my point was like 0, 360, and then 130, 360. I also need an origin point, 0, 0, and you need the mixture of those, 130, 0. So you have these 4 points, and then you have to make that into a rectangle, I suppose. So you can go ahead and grab your segment tool and you can say, okay, that's my original rectangle. How do I get a continued fraction out of this? And the general idea here is, okay, I'm going to take squares. How many squares fit in this? I'm going to try to fit the you fit the squares in a very custom order, so making sure that the smallest length of the rectangle is the size of your new square. You go ahead and grab your, let's go to more here. If you grab your regular polygon tool and say, okay, so if I click from B to A, and it has to be 4 vertices, a square, right? And you do that, okay, I can fit another square in there, so I can do that one more time. And I can't do it again, because if I do it again, it will go over, right? So that's not gonna work. I have to undo that. And I can do squares the next small size. So I can go from G to C and do that. And okay, that's as many as I can fit in. If I zoom in a little bit and I go from I to D, I can fit in 1 square there. And you might be laughing at me like, what are you doing? Or maybe you know exactly what I'm doing and you're like, hurry up and get to the point. But I'm just showing you my entire process. O to H, there's 4, R to Q, there's 4, and T to S, there's, all right, so that is filling up the squares with this procedure. And the way that you make a continued fraction with your rectangle and squares like this is, and I probably need to write a little bit. Maybe I can write with my algebra. The general idea here, I should have turned off auxiliary objects, but you do 1 over 2 plus 1 over 1 plus 1 over 3 plus 1 over 3. And that is the reduced fraction, of course, of 130 divided by 36. And these numbers, 2, 1, 3, 3, just came from counting the number of squares. 2 refers to the first 2 squares. 1 square of this next dimension means 1 square for the next dimension. That 3 right there means the next small size. There are 3 squares, 1, 2, 3, and the next small size was 3. The cool thing about partial fractions is if you start kind of unwrapping it from the bottom, if I get rid of 1/3 right there, it'll give me a close fractional approximation of 13 over 36. So I can go get rid of those and say 4 over 11 is a close approximation. You can actually test this as well, right? You can say, oh, that disappeared, but 4 over 11 is 0.4, whereas 13 over 36 was also, okay, I have rounding on. I should probably turn that off. Haha, silly Mr. Sindel, talking to yourself in the third person as well. So if I round to 10 decimal places, then we can actually see what's going on here. And I should also scroll to the top so we can actually see the numbers that I just typed in. You can see 4 over 11 and 13 over 36 are really, really close to each other. And if I go ahead and get rid of the 1/3 here, it will be another great partial fraction that will tell me, oh, 1/3 is another great approximation, because 1/3 is 0.33 repeating. And that's how you get partial fraction approximations. The cool thing about this is these numbers that I was seeing, the numbers that I was counting over here in my spirals, there were 36 spirals here. And then if I zoomed in here, there were 11 spirals. And if I zoom in even farther, there are only 3 spirals. Where did those numbers come from? Well, they came from the denominators of those fractions. There was 36, 11, and 3. And I'm like, whoa, it was getting a close approximation, like 4/11ths of a rotation means there's going to be 11 spirals. 13/36 of a rotation means there's going to be 36 different spirals. And that's where the numbers came from. So I said, okay, well, I'm going to push myself. I don't normally code with Python. I've done a few projects in the past. So can I do that same technique where you use squares to find those continued fractions, and then from those continued fractions make those partial fractions and find all of those denominators to predict? So if I type in a random number like 135, can I tell exactly how many spirals there will be? Okay, that was too easy of a number because it's like a special angle. What if I did like 127? Could I predict the number of spirals when I zoom in and out? Like, would I know that the most inner number of spirals right here is 3? Could I predict that? And I tried. I got up some Python, and this is my pretty terrible code, but there's lots of comments, so if you want to try to make it better, you can do that. And I did that. So I said, okay, let's go ahead and do something. Okay, what angle did I just try over here? It's going to really put me on the spot. 127 degrees. So I said, okay, if I do 100, why did I just forget the last number that I just said? 127. So 127, and I go ahead and run my code, and it does the squares method and gives me the continued fraction with a 2, 1, 5, and 21. And it says, okay, well, the best approximation, you'll eventually have 360 spirals because those are coprime. And then you'll have 17 spirals, and then you'll have 3 spirals, and then you'll have 2 spirals. And that smallest one is like, it's 50-50. It sometimes doesn't happen, and I'm guessing this one is going to be one of those cases where it doesn't happen. If I zoom all the way in here, I can't really see 2 different spirals, so that one is the one of the 50% that doesn't work. But then you can see, okay, there's 3 spirals, and then according to my program, there should now be 17 spirals, and I'm going to count this with you and see if that actually works. So if I zoom out far enough, I'm seeing these counterclockwise spirals, but if I zoom out far enough, I can see, oh, there's these other line spirals. So if you want to count with me, we're going to start up here where there's the undo button. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and then this line is back to the undo button. There are indeed 17 spirals, so that partial fraction is great. And if I zoom out far enough, I should get 360 different spirals, which I don't want to do. I don't want to count 360, but it's pretty cool that you can tell me a random angle, and I can tell you the number of spirals as you zoom in and out just based off of an angle. It's satisfying, and I haven't Googled anywhere else if this is already well known in mathematics, but I didn't know it, and I had a fun little discovery, so I'm making a video of my rabbit hole that I went down. The one kind of final note that made me think about phi, because in all the way back to Weihart, she's talking about phi is the most irrational number and it's the most efficient number for getting spirals. I'm like, okay, well, what happens if I do that? So I programmed it in, and I said phi is 1 plus the square root of 5 over 2, and then I turned that into a phi angle with it being nice and small. And I said, okay, what if I change A to my phi angle? Let's go ahead and look at that. And oh shoot, my list is a little bit too big, but there it is. There is my phi angle of a degree, which is like the improvement on that Fibonacci spiral from scratch. But I can zoom in and out now. You can see they do look the same-ish, I would hope. And I can zoom in and out, and I should be able to count the number of spirals. It should be really tricky. So now I should be able to predict. If I zoom in and out, I should be able to get Fibonacci numbers. Let's go ahead and test my program. Again, this is about 137.5. So if I do 137, and I'm just going to go, I haven't tested decimals. I assume it works, but I don't know. Let's go ahead and run this. You do get, check out these Fibonacci numbers, 2, 3, 5, 8, 13, 21, 34, 55, 144. So the program confirms it. And the fun thing is, if you look at the continued fraction, this is something that I've known for a while too. You should get 1, 1, 1, 1, 1, 1, 1, which is the way to show you that it converges very, very, very slowly, which means all of these are terrible approximations of phi. And I think the reason that this is a 2 at the beginning is because we did 360 minus 1/5 of a degree. I think if we had done here just like normal 1/5 of 360, and we get, oh gosh, it's gonna make my program go slow, 222.5. I should have memorized that from the Weihart video, but I think if I did 222.5, 222.5, and I ran that, then this should be exactly 1111111, and then this last number I rounded, right? It's 122.5, but this is an irrational number. It goes on and on forever with no pattern, so it has to end somewhere. So I decided it randomly ended at 2. So that does fit the math. But again, the main thing that I'm trying to say without going off on my tangents is it converges really slowly. Every single time that you have a spiral that spirals back and forth, when there's a big jump, when I've been playing with this, really big jumps between numbers, I notice that it typically takes a lot longer for you to zoom in and out before you see that. So when there's all these really, really small jumps in the numbers, it goes back and forth so fast, and that just feels like it's, again, using the Weihart terminology, it's the leaves knowing that if they move to a clockwise direction, then counterclockwise, and then clockwise, back and forth as fast as they can, they will get the most amount of sunlight as possible. And you see that with how close these numbers are, but then you can like visibly see that as you zoom in and out, like it all comes together, and you see, okay, they're spiraling clockwise here, like from this dot to this dot to this dot to this dot. And then if I zoom out just a little bit more, okay, now I can see these other lines that are like zooming out like this. So counterclockwise, where they come up like this, and if I zoom out even more, I can see a different spiral, and if I zoom out even more and more, you can see each of these new number show up. I just thought it was really cool. All right, I did end the video, but I wanted to actually have a better conclusion. This is the worksheet, the lackluster worksheet that I ended up creating. It does not have as much fun as I had, but it does make sure that students know how to count the correct number of spirals. I chose a random angle that I can't even remember off the top of my head, but if you zoom in, you can see there's one spiral on the inside that's going this clockwise direction. There's another clockwise direction with even more. I think there's like 8 or 9. I forget which number we counted. And then on the very outside, there's this counterclockwise spiral. I think there were 26 of them. And I'm just making sure that, hey, students, can you count the correct number of spirals? Because if you can't correctly count the number of spirals on this dot paper that is a little bit more obvious, there's no weird bumpiness in the way, then you're going to struggle with the pine cone. So we made sure that everyone is on the same page. We all know how to count correctly. The grades that I teach are 9th through 12th. And then we remind them what Fibonacci numbers is, Lucas numbers, or Luca numbers, some people pronounce it that way. And then we actually got out there and started gathering data. Again, the main question that we were trying to answer today, I guess yesterday, was, are Fibonacci numbers really common? And the answer is yes. Like, we had a hard time finding things that were not Fibonacci numbers. They were like, I found a pine cone that's 8 and 8, and they would say pine cone, pine cone, pine cone. But if you had other plants, you could say the name of that plant here. And we had tally marks, so they'd do 1, 2, 3, 4, and then they cross it for the 5. If they keep finding the same pine cone, it's an 8, 8, 8, 8, 8, 8. If they had an 8, 13, they would put that down here. And then the classification for the numbers was always a Fibonacci number. The only 2 students that found pine cones that were not a Fibonacci number of spirals were pine cones that were either so microscopic that you really couldn't count them correctly. There's human error, I'm sure. And then the other one, I think it just got stepped on, to be honest, and like squished it out of a Fibonacci number of spirals somehow. Or maybe it is a rare one. It wasn't a Lucas number either, so I'm not sure what happened. I haven't analyzed the data yet. I just collected it, and I'm basing everything I'm saying right now on my anecdotal data. We didn't even get down to the bottom questions, but I thought it would have been talked about. It would have been fun to talk about if we had enough time. I had a blast designing this lesson. My students had fun seeing that Weihart was not a liar, and seeing how there were all these spirals that they never knew existed. They're always 5, they're always 8, and maybe if we had a bigger pine cone, we could get a 13 number of spirals. This was a blast. I hope someone else can use this lesson too. The general idea is you prep them by watching some Weihart videos, you discuss it, and then that's day 1. Day 2, you actually go out into nature and you look for the spirals, you you just basically go through this worksheet, and then if you want to be cool, maybe you could do like a coding problem when they get back from school. You could have them do GeoGebra is probably not as fun, but Scratch is usually pretty user-friendly to try to get a spiral like this, or to make their own leaves and make that colorful. There's a lot of creativity that you could do there. And the spirals are pretty fun too. If they could make all 3 different types of spirals, that's pretty. I think that was the hardest thing that I did in terms of code. Thanks for watching, guys. I hope you took something away. Bye.